Thanks very much. I'm joined here with my colleague Adam Summers, and we'll be talking about a Solar Energy Technologies Office funded project, an ENERGISE project to do voltage regulation on distribution circuits using PV inverters. This work is a large collaboration between a number of different organizations, but the team here at Sandia includes Rachid Darbali Zamora, who's a student from the University of Puerto Rico, Maya West, a new postdoc, Javier Hernandez Alvarez, and a couple of staff members, Matt Reno and Cliff Hansen. So as many of you know, the cost of solar has been dropping over the last few years, and with that we see increased penetrations of solar PV installations. And as we install more solar, because power systems are very slow to evolve, we run into technical challenges that prevent additional installations. And these could be on the distribution system due to high or low voltages. They could also be at the bulk system level due to some sort of frequency challenges as you remove some of the inertial components from traditional thermal generators. But we believe that a big part of the solution has to do with advanced inverters, which are oftentimes called smart inverters. An example is shown here in the lower right. You can see it's a smart inverter because it's wearing nice glasses, so it's a very intellectual inverter. And then it also has the ability to communicate to grid operators. It has the ability to ride through different deviations on the power system, and it can support voltage and frequency by modulating its output. And so the questions that we're raising with this project have to do with the voltage side of things. So what is the best technique to provide voltage regulation to distribution systems? And how can we verify that these types of algorithms or these approaches will work with physical devices prior to field demonstrations? So just a quick note on kind of the physical challenges that we're working with here. Here are a couple of images that our colleagues in the north at NREL put together, Brian Palmatier and others, about traditional voltage deviations from a distribution substation down to customers. And typically you have loads out here and the voltage profile drops as you go out on the feeder, and toward the end you have the lowest voltage. And so there are components along that way, be it tap changers or some sort of cap banks to adjust the voltage on those systems to maintain voltage within a tolerance, typically referred to ANSI range A, which is plus or minus 5% in the United States. But in cases where you have large PV systems out on this feeder, that is injecting current flow into the feeder, and due to Ohm's law, you're essentially raising up the voltage because there's some impedance along this line. And you can exceed those ANSI limits, which is a problem for the utilities because it's a requirement in the United States. So the question is, how do you solve that problem? And we, again, think that the most cost-effective method for doing that is to use the PV inverters themselves to provide that voltage regulation. And so this is a good approach because it's cost-effective. You're not installing additional equipment. Utilities or other grid operators don't need to install anything. And it's logical because the equipment that's causing this increased voltage can be used to solve the problem. So it makes sense to correct for its own issues that it's creating, in essence. And so with this project, it is one of a number of different CEDO-funded ENERGISE projects. This one we've called the PODROMOS project, which is Programmable Distribution Resource Open Management Optimization System, which is a Greek term for forerunner, and I thought is very representative of what we're doing here about testing new algorithms for this voltage regulation. And so the goal is to use DER devices to perform ADMS functions by measuring the states of the system, performing some sort of state estimation, and then issuing optimal DER set points to the PV inverters themselves. And as you can see on the right, we're going through different stages of first running power simulations, then running real-time voltage regulation simulations using our OPAL-RT system. And then we're connecting in our case, 100 microinverters here at the Distributed Energy Technologies Laboratory to the power simulation to verify that when we work with physical devices that the algorithms continue to work, and then we have a field demonstration at the end of the project. The three different algorithms or voltage regulation methods that we're considering are shown here. The first is a fairly well-known method called Volt-Var, where you adjust the reactive power based on the grid voltage measurements of each of the devices. This is pretty simple, doesn't require communications. It's currently included in a number of the different interconnection standards in the United States, including the new IEEE 1547-2018 code. And the only real con with this is it doesn't reach the global optimum. It doesn't know, like, aside from its current point of interconnection, what the rest of the feeder or the system has in terms of voltages, and so it can't adjust its output based on the needs of the global system. Extremum Seeking Control is a little bit different. So I have another slide about the details here, but essentially this is a function that provides probing signals from each of the DER devices, and based on an objective function that is broadcast to the devices, they can individually adjust their output to trend toward the global optimum. And then the last piece, which we're working on primarily with this project, has to do with adjusting the optimal power factors based on a state estimation of the system to issue the global optimal set points to the devices. This requires the most communications. It has to know the states, and it requires the most sophistication in terms of running the optimization. But theoretically, it should provide the greatest solution. So very, very quickly on the ESC, or Extremum Seeking Control, here's generally the method that's used or could be used in the field. So we have a centralized control center, utility control center that gathers measurements from substations, micro PMUs, DERs, or some other devices, calculates an objective function. In this case, I have shown here just a quick equation that demonstrates that we want to minimize the deviation from the nominal voltage. And then that is either sent to the devices or communicated to the devices, or calculating the power factor directly at the utility control center and sent to the devices, a probing signal plus a trend line where it moves over time, either positive or negative in the reactive power plane to move toward the global optimum. And because each of the devices have a different frequency, they can decompose or capture their influence on the objective function that's being transmitted to them. And if you'd like more information, we've got a number of papers here along with some Python code that runs that algorithm. So the power factor optimization is shown here. What we're doing is we're issuing new power factor set points to each of the DER devices every minute, and optimizing over a 15-minute horizon using OpenDSS simulations. And so kind of the process flow is the IEDs, or intelligent electronic devices located on the feeder, capture data. In our case, we're using micro PMUs or simulated micro PMUs to capture that data. That goes to a Georgia Tech developed state estimation software called WinIGS, which then issues the voltage and current set points for each of the buses as another C37118 stream to a particle swarm optimization tool. And the particle swarm optimization calculates the loads based on that current and voltage phasor data, and it instantiates the DER forecast, power production forecast, based on a forecasting engine that we've developed, which uses a persistence model. That instantiates OpenDSS simulation, which we run over this 15-minute horizon, and using particle swarm optimization, we can change the power factor set points to each of the devices and move toward that global optimum, eventually issuing that through our software vendor company, Connected Energy, to either physical or simulated DER devices. Just real quickly, the optimization function in our case is to minimize this three-term equation. The first is if you have a violation, meaning you're outside ANSI range A. The second one is a standard deviation away from the base voltage or the nominal voltage. And the third is an economic component representing the cost, potential cost of curtailing active power to produce reactive power when you move away from unity power factor. This is, I just wanted to point out the devices that we've been using for these simulations, and we'll get to the results here pretty quickly. There's two different types. One is a simulated PV inverter. That's the EPRI PV simulator shown here, and this device has multiple advanced grid functions associated with it, and they can be adjusted using a DMP3 communication protocol that Connected Energy is communicating with. On the right is the 100 microinverters located out at DETL that have power factor settings that are plus or minus 0.85. And again, we can adjust the power factor set points of these devices through communications from Connected Energy using in this case, a Shakir shell or SSH communication mechanism. We're working with two feeder models. The first one is PNM, our local utility here in Albuquerque's PV model or feeder model that has three very relatively large PV sites that are utility owned, resulting in a 440% PV penetration level. And so those tend to drive a lot of the voltage on this feeder because there's relatively low load on that. The second model that we're using is a national grid model shown here in the lower right that we have artificially added distributed PV to reach 50% penetration level, which was required by the ENERGISE FOA. To convert these relatively high fidelity feeder models to something that we could run in OPAL-RT, we used a circuit reduction model, which is shown here with a couple of papers. And so in the end, we reduced these models to a much simpler set of equations, essentially. And so we've got 15 buses, for example, for this PNM model that started with multiple hundreds. And so we've simplified that. And so now I'd like to turn this over to my colleague, Adam Summers, to talk through our implementation of this technology with OPAL-RT and present our preliminary results.
Thanks, Jay. So this slide presents our particle swarm implementation. Jay's gone over this upper portion of the slide previously, so I'll go over the bottom part of this slide. In OPAL-RT, we have our 15-bus PNM feeder with 15 virtual PMUs that have been located into the simulation to give a better visibility for our particle swarm implementation. These measurements are sent to a local PDC where the data has been aggregated and sent to our Georgia Tech state estimator. After we get our optimal power flow set points, they are communicated back to Sandia, where either they're set with our local hardware, our microinverters, or our simulated PV devices, at which point the loop is closed for this simulation. So for the irradiance profiles here, we were provided by EPRI a bunch of different irradiance profiles that we then selected 3 of them. And from those 3 profiles, we then used a wavelet variability tool to smooth the data due to spatial averaging. We did this because a cloud passing over a 258 kilowatt site does not have the same effect as a cloud passing over a 10 megawatt site. The smooth data is presented here on the left that was used for our 3 simulated PV inverters. So this is our Volt-Var implementation versus baseline. As you can see, the baseline is average system voltage is indicated here in the solid blue line with a patchwork of maximum system voltage and a minimum system voltage in these light blue colors. The red line is the Volt-Var curve that we implemented. The curve that we implemented is shown here on the bottom left. This curve is less aggressive than we initially started with. We had a more aggressive curve in our first experiments, but noticed due to delays in debus, we were getting power system oscillations. This slide presents our Extremum Seeking Control results. This is our first communication-based voltage regulation scheme. As you can see from this slide that the ESC is able to drive the system to a 1 per unit voltage level. With additional tuning of these ESC parameters, we'd be able to tighten this voltage envelope around a 1 per unit, which would give us a better result than the previous example. This is our first pass at our optimal power flows particle swarm implementation. As you can see, we have some issues to work out with these peaks from the particle swarm. These seem to be due to the particle swarm arriving at erroneous power factor set points. But in points where you can see down here where the solution is driving closer to 1 per unit, which acts with less oscillations than the extreme seeking control method. And here's a comparison slide of all 3 methods being employed, and you can see the advantage of not having communication in the voltage regulation in the red lines versus a communication-based extreme seeking control method. And then if you're able to incorporate communications with state estimate, you can get a even better resolution into getting that 1 per unit voltage regulation. And with that, I'll pass it back to Jay.
Yeah, awesome. Thanks, Adam. I should note that those results of the particle swarm optimization are hot off the press from yesterday, so we're still working through a little of the challenges here, but I think that highlights the advantage of using hardware in the loop and real-time simulations, as you can track down those issues prior to demonstrating them in the field. And so our next step over the next couple of months is to start running these 3 different methods in a live feeder. This feeder is in Massachusetts, and we're going to be controlling 28 PV inverters at a 672 kVA PV site. And so we've got a pole-mounted feeder monitor that will be capturing voltage and current information at that feeder at a different location, and so we can compare the methods. Of course, you don't get the same irradiance every single day, and so there's going to be some variability, and we're hoping to use statistical means to demonstrate that one method is superior to the others. Just one note on the Extremum Seeking Control, the particle swarm optimization for that live feeder site. What we have is a problem here because we don't have a whole lot of information from the field, right? So there's limited micro PMUs out there. We don't have many DER devices that are sending information to our state estimator. And so what we're hoping to do is, as opposed to using pseudo measurements that include historical data, actually use the real-time simulation itself to provide the data necessary to solve the state estimation and then run the particle swarm optimization and send the set points out. And so as we send the set points out to the physical PV site, we'll also be sending those set points to the virtualized device that will be running here at Sandia that's connected to the OPAL-RT system. And with a reasonable approximation of the loads and a reasonable estimate of the PV production, I believe we'll be able to get, pretty close to the power factor set points that we need to minimize that fitness function. So real quickly, in conclusion, we've found that Power Hardware in the Loop and real-time experiments and simulations have provided us a lot of confidence in deploying these different techniques. The same communication challenges that are faced with real physical devices can be represented in the Power Hardware in the Loop environment. Errors and challenges that we've seen, for instance, the issues with the PSO not hitting our global minimum, can be remedied, and we'll be capable of feeling confident by running the same feeder model here at Sandia prior to deploying these technologies out in the field. In terms of the techniques themselves, Volt-Var is a very effective method. There's historical data for probably a decade now that this is a very stable and effective approach, especially with a reasonable deadband. Extremum Seeking Control is something pretty new. It has a lot of benefits because you don't need information from the feeder beyond what you can communicate to and from the DER devices. And so that's like kind of an intermediary step that you could potentially use to get to a global optimum. And then lastly, the state estimation-based model-fed DER optimization technique can be used in the future with enough data coming from the field. And in our case, I think we're going to try to do this with the digital twin concept. But in the future, when you have ubiquitous micro PMUs or other devices out there, we'll be able to use these types of approaches to send precise power factor set points to large and small PV sites to reach the global optimum. So with that, I'd like to say thanks. I look forward to the questions at the end, and I'll pass it back to you, Matthew.
Thank you, Jay and Adams. Actually was a really good presentation.